An ungrounded neutral wire in a delta-wye transformer system presents several potential hazards and operational issues. Firstly, electrical hazards can arise. Ground faults on the line to neutral circuits can lead to high voltage buildup on the neutral wire, creating a significant risk of electric shock to both equipment and personnel. Overvoltages on the neutral wire can also damage sensitive appliances and electronic devices connected to the system. Secondly, system unbalance is a concern. An ungrounded neutral wire can cause current imbalances on the line to neutral circuits. This results in uneven loading of the transformer phases, reducing the transformer's overall efficiency and potentially shortening its lifespan. Thirdly, voltage fluctuations can become more pronounced. The neutral wire serves as a crucial reference point for voltage regulation. Without a solid ground connection, voltage fluctuations on the line to neutral circuits may increase, negatively impacting the stability and performance of connected electrical devices. Fourthly, ground fault protection is compromised. Ground fault protection devices, such as ground fault circuit interrupters, rely on a properly grounded neutral wire to function correctly. These devices detect ground faults by monitoring the current flow and tripping the circuit to prevent electrical shock and damage. An ungrounded neutral wire prevents these devices from operating as intended, leaving the system vulnerable to ground faults. Fifthly, code violations may occur. Most electrical codes mandate that the neutral wire of a delta-wye transformer be solidly grounded to ensure safety and proper system operation. Failure to comply with these codes can result in fines, penalties, and potential liability in the event of an electrical accident. Solidly grounding the neutral wire of a delta-wye transformer offers several benefits. Firstly, it eliminates electrical hazards. Ground faults are safely conducted to ground, preventing high voltage buildup on the neutral wire and reducing the risk of electric shock. Secondly, it improves system balance. Symmetrical loading of the transformer phases ensures efficient and reliable operation, maximizing the transformer's lifespan and minimizing energy losses. Thirdly, it provides voltage stability. The neutral wire provides a stable voltage reference, minimizing voltage fluctuations and ensuring consistent performance of connected electrical devices. Fourthly, it enables effective ground fault protection. Ground fault circuit interrupters and other ground fault protection devices will operate properly, ensuring safety and preventing electrical damage in the event of a ground fault. The recommendation is to solidly ground the neutral wire of the delta-wye transformer to address the potential dangers and improve the safety and reliability of the electrical system. It is crucial to have this work performed by a qualified electrician in accordance with all applicable electrical codes and safety standards. To delve deeper into the technical aspects, let's consider the underlying principles of a delta-wye transformer and the role of the neutral connection. A delta-wye transformer is a type of three-phase transformer that transforms voltage from a delta-connected primary winding to a Y-connected secondary winding or vice versa. The delta connection on one side provides a stable voltage source, while the Y connection on the other side allows for a neutral point to be established. The neutral point is the common connection point of the three Y-connected windings and is ideally at zero potential with respect to ground. When the neutral point is solidly grounded, it provides a low impedance path for fault currents to flow back to the source. This lower impedance path is essential for the proper operation of ground fault protection devices. In the event of a ground fault, such as a short circuit between a live conductor and ground, a large fault current will flow through the grounding system. This fault current will quickly trip the overcurrent protection devices, such as circuit breakers or fuses, isolating the faulted circuit and preventing further damage or injury. Without a solid ground connection, the fault current may not be large enough to trip the overcurrent protection devices, allowing the fault to persist and potentially escalate into a more serious hazard. The absence of a solid ground also affects the voltage distribution within the system. In a balanced three-phase system, the voltage between each phase and neutral is equal. However, if the neutral is not grounded, the voltage between each phase and neutral can become unbalanced, especially under unbalanced load conditions. This imbalance can lead to voltage sags, swirls, and other voltage disturbances that can negatively impact the performance of sensitive electronic equipment. Furthermore, the ungrounded neutral can become a source of noise and interference in the electrical system. Straight currents can flow through unintended paths, creating electromagnetic interference that can disrupt the operation of nearby electronic devices. The National Electrical Code, known as NEC, provides specific requirements for grounding electrical systems to ensure safety and proper operation. Section 250.20 details the requirements for grounding alternating current systems, including delta-wye transformer systems. It mandates that the neutral point of a Y-connected system be grounded under certain conditions. The specific grounding requirements depend on the voltage level and the type of system. However, in general, the NEC requires that the grounding system be designed to provide a low impedance path for fault currents to flow back to the source. This is typically achieved by connecting the neutral point to a grounding electrode system, which consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode system must be sized appropriately to handle the maximum fault current that could flow through the system. In addition to the NEC, other standards and guidelines provide recommendations for grounding electrical systems, such as the Institute of Electrical and Electronics Engineers, known as IEE, Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, commonly known as the Green Book. This standard provides detailed information on grounding principles, grounding methods, and grounding equipment. When grounding a delta-wye transformer, it is important to consider the size and type of grounding conductor. The grounding conductor must be sized according to the requirements of the NEC and must be able to carry the maximum fault current that could flow through the system. The grounding conductor must also be properly installed and protected from physical damage. In some cases, it may be necessary to use a ground fault relay to provide additional ground fault protection. A ground fault relay is a device that detects ground faults and trips a circuit breaker to isolate the faulted circuit. Ground fault relays can be used in conjunction with ground fault circuit interrupters to provide comprehensive ground fault protection for electrical systems. When selecting a ground fault relay, it is important to choose a relay that is compatible with a specific type of electrical system and that meets the requirements of the NEC. The relay must also be properly calibrated and tested to ensure that it will operate correctly in the event of a ground fault. It is important to note that grounding is not a substitute for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Grounding is designed to protect people and equipment from ground faults. Both overcurrent protection and grounding are essential for ensuring the safety and reliability of electrical systems. When troubleshooting grounding problems, it is important to follow a systematic approach. Firstly, inspect the grounding system for any loose connections, corrosion, or other signs of damage. Secondly, test the grounding system using a ground resistance tester to verify that the grounding resistance is within acceptable limits. Thirdly, check the voltage between the neutral point and ground to ensure that it is close to zero. Fourthly, use a clamp-on ammeter to measure the current flowing through the grounding conductor to verify that it is within acceptable limits. If any problems are found, they should be corrected immediately by a qualified electrician. When working on electrical systems, it is important to follow all safety precautions. Always to energize the circuit before working on it. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Follow all applicable electrical codes and safety standards. If you are not qualified to work on electrical systems, hire a qualified electrician to do the work for you. In summary, solidly grounding the neutral wire of a delta-wye transformer is essential for ensuring the safety and reliability of the electrical system. It provides a low impedance path for fault currents to flow back to the source, enables the proper operation of ground fault protection devices, stabilizes the voltage distribution within the system, and reduces the risk of electrical shock. Failure to ground the neutral wire can lead to electrical hazards, system imbalance, voltage fluctuations, and code violations. If you have any concerns about the grounding of your delta-wye transformer system, consult with a qualified electrician to ensure that it is properly grounded and meets all applicable safety standards. Remember to always prioritize safety when working with electrical systems. Always follow proper procedures and use appropriate personal protective equipment to prevent electrical shock and other injuries. If you are not qualified to perform electrical work, hire a qualified electrician to do the work for you. The information provided is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before making any changes to your electrical system. The National Electrical Code is a comprehensive set of standards for electrical installations. It is updated every 3 years to reflect the latest technological advancements and safety practices. It is essential for electricians and other electrical professionals to stay up to date on the latest version of the NEC to ensure that their work complies with the current standards. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It provides detailed requirements for the design, installation, and maintenance of electrical systems. Compliance with the NEC is essential for ensuring the safety and reliability of electrical installations. In addition to the NEC, there are other standards and guidelines that provide recommendations for electrical safety, such as the National Fire Protection Association, known as NFPA 70E, Standard for Electrical Safety in the Workplace. This standard provides requirements for safe work practices to protect employees from electrical hazards. It covers topics such as lockout/tagout procedures, personal protective equipment, and arc flash protection. Compliance with NFPA 70E is essential for protecting workers from electrical injuries. Electrical safety is a shared responsibility. Everyone who works with or around electricity should be aware of the potential hazards and take steps to prevent accidents. This includes following safe work practices, using appropriate personal protective equipment, and reporting any electrical hazards to the appropriate authorities. By working together, we can create a safer environment for everyone. Remember that electricity is a powerful force and should be treated with respect. Always follow safety precautions and consult with a qualified electrician if you have any questions or concerns about electrical safety. The information provided in this narration is intended for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before making any changes to your electrical system. The grounding of a delta-wye transformer neutral is a critical aspect of electrical system design and safety. It is important to understand the implications of not solidly grounding the neutral and to take steps to ensure that the system is properly grounded in accordance with all applicable codes and standards. By doing so, you can protect people and equipment from electrical hazards and ensure the reliable operation of your electrical system.